All right, crew, thank you and welcome back. We're going to go through some examples now for those equations of lines in 3 dimensions, which we had introduced in that last lecture. Okay, so let me go ahead and share my document camera. All right, so going ahead and getting started with that section from 12.5, right? Our equations of lines, right? And again in 3D. We'll do the planes portion in the next lecture, okay, to finish out this 12.5 discussion this week. But looking at this, right? So in our 3-dimensional coordinate system, that rectangular Cartesian coordinate system, right? When we look at some line traveling through that space, whatever it might be, similar to our lines in 2 dimensions, well, we need to make sure we can identify some point, x naught, y naught, z naught, some initial starting point, right? We'll say like when t equals 0, all right, we're going to start to track that line. So we need a point, and we're going to need the direction, right? So kind of like our slope, we're going to need this direction vector we'll call v for that line. And I start to identify that basically those components, let me zoom in here, A, B, and C, those are like our slope values, okay, for the direction of the line, how much we're changing the x direction, how much we're changing the y direction, z direction. Positive, right, where it means we're going increasing. The x values are getting bigger as we progress in time, as we track that line. Negative, we're going downwards, we're decreasing. Trying to compensate that. Think about that in 3 dimensions. Okay? All right. And so, depending on what point we find, what point we're looking at, right? The way we track, again, I think of like kind of like astronomy. Think of how like we might track the direction that a comet is moving through the sky, a plane even through the sky, right? If we're doing that. Our vantage point, the way we look at it, it might be a little bit different than someone, across the country, someone in a different city, okay? Even like a different street than we live on. But it's still tracking that same line in space as a whole, okay? But where we start to track, where we start to look, our initial point of reference, or maybe the time that we need to see, right after 1 second is going to be here, maybe someone else is going to be 3 seconds later, whatever it might be, okay? So those all might be different, all right? And so the way we write that equation for a line, we can imagine it with 2 pieces, okay? So as a kind of vector form, of that line, r of t is going to be this r naught, right? Or r is kind of this radial distance. If I was to point from the origin to that line, that's going to be my r of t, okay? At this time, I'm pointing to the line. That's where we are. When t equals 2 seconds, I'm pointing over here. R naught, right? Our initial location plus that parameter t times v. Okay? So it's going to look like that x naught, y naught, z naught vector pointing from the origin to where we're starting, plus some parameter t times our direction vector ABC, right? Kind of adding those together to give that new location. Okay, and here t, our parameter. Okay. And then we saw from there our parametric equations, basically separating these components, that if I want to find my x location, it's going to be x naught plus a times t, or t times a, up to you. The y naught plus bt, z naught plus ct. Okay? And that parameter is just some general kind of how we're looking at, how we're tracking the location on line, right? We can have the same line using a different point with a different parameter even, following that same direction, right? But maybe the initial point is different, and that parameter, right, how quickly we're, or how much space we're putting between those points might be different. Okay? And so in this case, I'll say this can be the same line, mapping out all those same points, but starting at a different point and using a different parameter, right? A different timestamp. You can look here at, after 5 seconds and see that point. Your friend down the hill, down the street, is going to look there after like 10 seconds, whatever it might be. Okay? Depending on the equipment you're using, like think about telescopes tracking, one's going to have to like track more rapidly. A smaller field of vision is going to have to move a lot more. A wider field of vision might not need to track as fast. It can kind of slowly pan and gain a bigger scope and see that line trajectory, whatever it might be, that kind of aspect. Okay? But in the end, we can still map out all those points and produce that same final line regardless. And our x, y, z components can be computed individually. And then if we're using the same time, right, we're not going to go faster in the x direction than the y direction. These parameters for a single line all have to be consistent, right? S is going to be 1 throughout, 2 throughout, 3 throughout, whatever value you might want to get those particular ordered triples, x, y, z. Okay? So those t's have to be equivalent. We'll get our symmetric equations for that line. The x minus a over, x minus x naught, sorry. Subtracting that over, divide by a, y minus y naught over b, z minus z naught over c. There we go. So in this format, denominators are our direction vector. Remember, it starts off as x minus, so kind of like our slope function, our slope equation back in algebra. Building up some of those equations before, it always starts off with that subtraction to begin with. So when we extract the information, we have to remember to change that sign. Okay? Sorry, get my finger out of the way. All right. So let's look at some examples then. All right. Here we go. So just borrowing these from the book. Do a couple here. So for example, let's check out here, say number 4. This is on page number 871. All right. And it says here, find a vector equation and parametric equations, parametric. For the line. And we have here in this information that is going to be the line through this point, 0, 14, negative 10, and is parallel to the line given by x equals -1 plus 2t, y is equal to 6 minus 3t, and z is equal to 3 plus 9t. There we go. A lot of detail there. So similar, again, I tied this back to a lot of previous courses, like our algebra, writing equations for lines, right? Even calculus 20A, writing equations for our tangent lines, so on there, okay? All right, so in this case, we want to go through this point. There's my x naught, y naught, z naught, okay? And now here, if we're parallel, that means we're going to have the same direction vector. Okay, the same slope numbers, right? The same direction. We're moving the same direction for these two lines. Just like parallel lines back in algebra. So now as we look at this, our value for A, 2, B, right, our Y direction number, -3, and C, +9. In the future, if you desire, if these were kind of like scalar multiples, we can factor out a number. You're still moving the same direction. It's just maybe a shorter vector instead. I don't know, my hands are all weird. Shorter vector, right? We can lengthen it, make bigger jumps, whatever it might be. So had this been like +3, -3, 9, we could factor out a 3. Have that same direction, but just a shorter vector, perfectly fine as well. If you want to get really fancy, you can take that direction vector and you can make it a unit direction vector, v hat, if you want. Find the magnitude, divide, all up to you. Okay, but for simplicity's sake, just straightforward, plug in numbers, not worrying about doing too much extra. Just the fact that we want to pass through this point, be parallel to this line, have the same direction vector. Here we go. So for our vector equation, remember r of t as a vector, r naught plus t times v, right? So in this case, our r of t is going to be equal to r naught. So as a vector, our location, our initial point, 0, 14, -10, plus our parameter t, sneak that in green, times our direction vector, 2, -3, 9. So I'm perfectly happy leaving it this. I'm not sure what the back of the book says. Okay. Another option, if we start to do that addition, 0 plus t times 2, that just looks like 2t. 14 plus t times -3, 14 minus 3t. -10 plus 9 times t. That could be another option. Perfectly happy with both of those. So for any t we choose, plug that in, right? The same t throughout, or s if you want to use that parameter, right? That's just some generic independent variable we're going to utilize. We can find any point on that line. When t equals 0, we're at our initial point, and then we can start to plug in other quantities for t and get more and more points. And that vector is going to point us from the origin, point you exactly where we need to be. Okay. All right. So there's the vector equation. Our parametric equations. Right? Those are the three. That system, let me slide this up. X naught plus AT, Y is Y naught plus BT, Z is Z naught plus CT. And so basically we're just taking those components, right? And it's identifying, okay, this is how I'm getting my X, this is how I'm getting my Y, this is how I'm getting my Z. All we're really doing is transferring from that vector form, okay? X is going to be 0 plus 2t. We'll simplify down and just call it 2t, just like we did up here, okay? And again, if that's confusing, troublesome at all, let me know. Email me, let me know. We can put that 0 plus 2t if you wish. The y, 14, y naught, plus b times t, negative 3t. And again, I should have made that 14 minus 3t like we saw here. And z is going to be z naught, negative 10, plus ct, 9t there. And so maybe this one, just to be clear, I'll put the 0 plus 2t, and then simplify over here just to make it look nicer. There we go, better. And we, even though it didn't ask for it, we can even do our symmetric form, our symmetric equations. I know it didn't ask for it, but bear with me. Our symmetric equations, x minus x naught over a, y minus y naught over b equal to z minus z naught over c. So all those ratios equivalent. X minus 0 over 2, or just x over 2. Y minus 14 over negative 3. Watch that sign. Z minus negative 10, so z plus 10 over 9. Okay, and again, you can make this just simply x over 2. The big idea, like I mentioned before, that when we take these symmetric forms and start to extract that initial point out of it, that initial location, doing the opposite signs, well, in this case 0 if that wasn't there, if you don't have a number, that's 0, positive 14, negative 10 for the initial location. Okay? All right. Okay? All right. So with that said, there's that example. Again, more straightforward. Given a point, given a direction, build our equations for that line. Okay? In those different formats. So next up, pardon me. Next up, let's look at this equation, this problem. Number 14, still the same page, 871. And in this case, is the line through negative 2, 4, 0, and this point, 1, 1, 1. So the line connecting or passing through those 2 points, is that line perpendicular to the line through these points 2, 3, and 4, 2, 3, 4, and 3, negative 1, negative 8. So in this problem, we can imagine building our equations for 2 lines. This is one line passing through those 2 points. The second line passing through these 2 points, right? So here, line 1, line 2 information. Okay. We can do the work like we did for that problem number 4. Build those two equations. But the big statement, are these two lines perpendicular? So perpendicular, right? They're going to intersect at a right angle, or in our terms, this is the same thing as saying, are these orthogonal? And going back to some of our work, I think it was 12.3, right? If we're orthogonal, if we're perpendicular, that means that the dot product equals 0, right? So in this case, we're going to ask, is the dot product of our direction vectors zero? Right? The direction that we're moving, those vectors pointing us, is the dot product going to give us 0? Are those direction vectors, line 2, line 1 direction vectors, are they going to be intersecting at a right angle? If we don't get 0, that might mean they intersect at a different angle, whether it be acute angle, obtuse angle, right? That's a non-zero. And we'll talk about a little bit of other cases, right? That maybe the lines can be parallel if those direction vectors are scalar multiples of each other, or something else. And again, it's kind of hard to show. They might be skew, right? Two lines that aren't orthogonal, they aren't going to be at right angles, but they never touch either. And that's going to be skew. We'll talk about that in just a moment. Focus on this problem real quickly. Parallel would be that the direction vectors pluralized direction vectors are equal, right? That's what we had in that problem number 4, the same direction vector or scalar multiples of each other. Okay, so that's just a little aside. We'll have a third option in just a moment. But we're focused on perpendicular, right? That the dot product of our direction vector is going to be 0. All right, so here we go. Let's look at this information. For line 1, our 2 points, -2, 4, 0, and 1, 1, 1. So for our direction vector, I'm going to call it V sub 1, right? That A sub 1, B sub 1, C sub 1. That's going to be, if this is my X1, Y1, Z1, X2, Y2, Z2. Forgive me for all the subscripts labeling, right? For this first line's direction, just like we'd find the slope, the change, rate of change in the X, Y direction. In 2D, we do the same thing in 3D. We're going to do X2 minus X1, Y2 minus Y1, Z2 minus Z1. Right? So for my first direction vector, 1 minus a -2, 1 minus 4, and 1 minus 0. And that first direction vector, +3, -3, 1. Double check my arithmetic, make sure I'm not moving too fast. Line 2. Our 2 points here, 2, 3, 4. And our second point, 3, -1, -8. Make sure I get that sign. Good. So again, x1, y1, z1, x2, y2, z2. Our second direction vector, again, x2 minus x1, y2 minus y1, z2 minus z1. I know a little redundant, but just to be clear, 3 minus 2, -1 minus 3, -8 minus 4. So my direction vector here, 1, -4, -12. Whew, big one there. Okay. So considering those two vectors, I know we're focused on whether or not these two lines are perpendicular at the moment. So we're going to be definitely checking that dot product. But as we start thinking about some of those other cases, are they parallel? I should kind of consider if they're going to be parallel, then I can take the same constant, the same scalar, distribute it in to get the same end result, right? That this vector can be equal to this or vice versa, right? And so thinking about it, like if I want to get from 3 down to 1, I would divide by 3, right? Or multiply by 1/3. But if I do that for the other two, -3 times 1/3, -1, that's not -4, right? So that's not going to work. So they're not going to be scalar multiples of one another. So they're not going to be parallel. Okay? But for them to be perpendicular or orthogonal, if I take the dot product, is that going to be equal to 0? That's going to be perpendicular or an orthogonal. Again, use that language. Okay? This other way. So doing so, our two vectors, 3, -3, 1, dot with 1, -4, -12. And so that dot product, doing this product, again, sorry for all the clicking here, 3 times 1 plus -3 times -4, right? Multiplying component-wise and adding those results, plus +1 times -12, 3 plus 12 minus 12. All right, those look good. They cancel out, but we're still left with that 3 up front. So the dot product's not 0. That means the lines are not perpendicular. They're not orthogonal. Okay. Got it? All right. So extending this, and this is going into some of the problems like numbers 19 through 22 on that same page. Rather than starting a new problem, let's work on this one, kind of extend it. Okay, so parallel, we have that idea that they kind of, right, run and never in the same direction, never intersect, right? orthogonal. They're going to cross each other at a right angle. They intersect at a right angle, those direction vectors, okay? Or even here, maybe they kind of, the direction vectors are orthogonal. They're perpendicular. They run at 90 degrees to one another, okay? But in this next discussion, we can also discuss skew lines, right? These are going to be lines that are not parallel and never intersect. So I kind of think about it like having these two lines on two different levels. Okay, and again, I know with the dot cam and whatnot, it's a little harder to see, but there's something like this. We have one line coming up this way, another line dashing down this way, but they're never going to touch. They might not be orthogonal, perpendicular to one another. They can form an angle, but they're never going to intersect. And going back to the last problem, we might have lines that are orthogonal, like they run perpendicular to one another, their directions, but maybe they don't even intersect. We're going to have perpendicular lines that do intersect, okay? But it doesn't even have to. So now this question comes in then, right? How can we check if two lines will ever intersect, right? Or if the lines will be skew lines. Okay. And so in that language, in that discussion, okay, for those lines to intersect, right, if the lines intersect, the lines will share a common point. Right, there'll be some x, y, z order triple that both lines will pass through, that they'll both share. Okay? So now, in that discussion, kind of like what we had before, if I can draw this, okay? So you might have this first line with our parametric equations. Okay, some initial point. But then we might have this second line coming in, and of course have a point of intersection. Okay. And for that second line, it might not have the same initial point, of course, right? That point of intersection might not be the initial point. So let me call it x1, y1, z1. So it's the different initial point, the one point we know. And likewise, right, where we're looking in time might be different. And I kind of think of these particles moving, right? This particle might be moving really fast, zooming across. This particle might be taking its time. But at some point, right, they might cross the same path. They might impact, right? But depending on which line we're looking at, which particle we're tracking, how quickly we're scanning, what time it is we're looking at might be different. So we might need to use a different parameter. So I'm going to do a different direction even. So DS, ES, FS. I know it's a lot of extra labels now, but in this case, my direction vector DEF, right? My parameter is S. Okay, up here, what we had done before, hopefully those still are clear. Direction vector ABC, our parameter T, okay? Initial point, so on. So if we want to see if these two lines are going to intersect, they're going to have a common point, right? So to check if the lines intersect, we need to see, right? We need to check if the X, Y, and Z components ever all match, right? So the X coordinate from one line matches the X coordinate from the other. So in this case, right, basically we're seeing this L1 ever equal L2 for some point. And then again, that's a very simplistic, overly simplified notation here, but hopefully that concept makes sense. We're going to check, does X naught plus AT, is that ever going to be equal to X1 plus DS? And Y naught plus BT, and while I'm here, Z naught plus CT, do those match up to our Y1 plus ES, Z1 plus FS, right? So for the same T and S values, do all three X, Y, Z match? That's what we're kind of working on. I know, a lot to set up there, okay? So going back here, and we can, depending, see another example, okay? So from our problem, all right, so here, from number 14, our L1, right? That line, I know we didn't write it, we found our direction vector. We had our point, or a point, but we can look at here, X is going to be -2 plus 3t. Y is going to be 4 minus 3t. Z is going to be 0 plus 1t. Okay, so from one initial point, and you could have done the same thing with this point if you wanted. This point, that direction vector, A, B, C, X naught, Y naught, Z naught. My second line, we'll do the same thing. X is going to be 2 plus 1t, or 1s, sorry, now make sure I change my parameter. Y is going to be 3 minus 4s, Z 4 minus 12. S. Changing my parameter, but there's our 2 lines. Okay. So now we're going to start to work on, can I get a value for S and T such that when I plug in, S is 1, T is -2, whatever it might be, that the X's will match. And when I plug in those same values for S and T, right, S is 1, T is -2, Y's will match. Same thing for Z. Okay? Can I get those to work? And so when we look at that, well, we're going to check if they're going to intersect. Will these lines intersect? Okay. Are those lines going to intersect? We're going to try to solve this system, right? That -2 plus 3t is going to be equal to 2 plus 1s, or just s there, right? We'll simplify that down. 4 minus 3t is equal to 3 minus 4s. And for the z, 0 plus 1t, or t, is equal to 4 minus 12s. All right, so we have these 3 equations. Here's for the x's, the y's, the z's. Are those 3 going to match up? And what we can do, start off with work with any pair of equations. Okay, and so for instance, we can do the x and the y. We can have probably more easily done the z with any of those. Okay, but let's do it this way. All right, so if I do that here, -2 plus 3t equal 2, and again, I'm going to not write this in color coordinating in just a moment. The y, what am I at, 4 minus 3t equaling here 3 minus 4s. And out of, kind of common habit with algebra, bringing all my variables to one side, constants the other, I can make this the same as like 3t minus s. Subtracting s over, add that 2 over is equal to 4. -3t plus 4s is equal to, subtract that over, -1, right, for instance. And if we were to solve that system, right, adding down 3s is equal to 3. So s equals 1. And so if s equals 1, back to the top equation, 3t minus s equals 4. So 3t minus 1 is supposed to be equal to 4. 3t is equal to 5, or t is equal to 5/3, right? Some weird fraction, but that's perfectly fine. And so we can see with some steps here, with these 2 values for s and t, both the x and the y's will match up. Okay, so that's what we've just determined. With s equals 1 and t equals 5/3, we can check both the x and y values, right, will match for each line. Okay, the x and the y components will coincide. The x value from line 1 will be the same as the x value on line 2. The y value for line 1, the same as the y value on line 2. With those plugging in, you can check. I'll leave that to you. But in order for those lines to intersect, the lines intersect, the z values will match too. So remember those z's, right? For the line 1, z was equal to 0 plus 1t. Line 2, z was equal to 4 minus 12s. So with s equals 1, t equals 5/3, plugging in, t was 5/3. Already I'm seeing this isn't going to work for me, unfortunately. Right, so on line 1, my z coordinate 5/3. The z coordinate here, 4 minus 12, -8. So those don't match, right? So that's that idea. The x and y values might link up, but the z values, right, the height of those lines, totally different. If we got those two to match, both of them being 5/3, both of them being -8 or whatever number, that would have meant both the x, the y, and the z all coincide. Let me get that up there, sorry. They all coincide. They're all going to link up, match. But when I get one of those values to be different, the z value, right? So they might line up in the x and y, but when you tilt it in the z direction, totally off. Or whatever value doesn't match up. Whether the x's don't line up, the y's don't line up, whatever it might be. Okay? All right. So in this case, since those don't match, values do not match, these lines will not intersect. Okay, if they did intersect, x, y, and z would all match, and we'd have exactly what parameters, what instance in time we need to look for those two to have the same x, y, z values. All right, I'll leave it at that. Next lecture, next discussion, we'll start to talk about the equation for planes, okay? I'll stop sharing these notes. This lecture will be online throughout the semester. If you have any questions, concerns, definitely feel free to email me, contact me. We'll have office hours Mondays and Wednesdays. I'll put that information on the Canvas page and send you a notice. Okay, so you can start to follow along with those as well. In case you have questions, we can meet through Zoom there. All right, take care. See you all soon.